Hello, this is Tripoli 41 Lecture 11, where we'll discuss non-ideal PN junctions, including junction breakdown and the capacitances, and eventually we'll draw the small signal model of the diode. So our objective for this lecture is to identify breakdown mechanisms in PN junctions, plot the IV curve of a non-ideal PN junction, or add the non-idealities in our IV curve, compute and plot the parasitic capacitances, and eventually model the diode at small signal. Let's start with our ideal diode as expected or predicted by the Shockley model equation. Here we have the plot of the IV curve, and we know that at forward bias, the current increases exponentially, whereas at reverse bias, the current saturates and approaches a value minus I naught. Since at enough reverse bias, this term here approaches 0 and we're left with minus I naught. Now this equation tells us that as VA approaches negative infinity, then we'll just maintain the value minus I naught. However, in real life, when we apply enough reverse bias to a diode, we actually get to a new region of operation where the diode breaks down. Okay, so this breakdown region does not actually mean that the diode is already broken or cannot operate normally anymore. What actually leads to the diode being unusable is too much current that it heats up and burns. However, if we get to this breakdown region and we at a controllable rate or at a limited current, then the diode can still go back to its normal operation, given that we apply the voltage at this range. So this breakdown region starts at this minus VBR. So we take VBR as a positive value, and that's the breakdown voltage of the diode. Now, some diodes are actually designed to operate in this breakdown region. So most of the time in circuits, Zener diodes are actually reverse biased enough such that they are in the breakdown region. What's the main application, or why do we want to be at the breakdown region? It's because the slope here is actually steeper than the slope here, and therefore in terms of our approximation, this actually looks like a constant voltage source more than this region here. So if we want the diode to look like a voltage source, the region here is actually better. Now, how do we determine that breakdown voltage, or where does it depend? Now, if we apply some reverse bias, that's why there's a negative sign here, that is large enough, the electric field actually increases until it exceeds some critical value ECR, or the critical electric field. When the electric field exceeds this value, the junction will enter a breakdown mode where suddenly a large reverse current will flow. Now, there is nothing actually very new to this equation right here. We just equated, or this equation right here is actually from Emacs. So we just equated that Emacs is equal to ECR, and then this is our usual equation where this normally is VBI minus VA. However, we are noting that this critical electric field is reached at VA is equal to minus VBR, and so we end up with this new or seemingly new equation right here. Now if we manipulate the equation and solve for VBR, we'll get this one. So given that we know the critical electric field and the doping concentration at the lightly doped side, so this one is the doping at the lightly doped side, and we are actually assuming for this equation and actually this equation as well that we have a step one-sided step junction, and also given this n here, we can actually solve VBI. So VBI is also a function of this n. The diode enters a breakdown region through what we call breakdown mechanism. So the first one that we'll discuss is what we call avalanche breakdown mechanism. Now before going through that, let's review first or look first at how the carriers cross or travel through our material when under some small electric field, some small reverse bias, wherein the device is not yet in breakdown. So we actually drew the carrier to be drifting from this point to this point through a smooth transition in energy. However, what actually happens is that this electric field here accelerates this carrier, this electron, and at some point the electron will bump into the crystal and it will lose some kinetic energy, and that kinetic energy is transformed through heat within the crystal. So the acceleration and the transfer kinetic energy happens on multiple steps until this electron gets to this point. However, when we have some very high electric field, a strong electric field, then the faster that accelerates this electron faster and gives a larger kinetic energy prior to bumping. Now the kinetic energy again is measured from this point to EC. So if this kinetic energy is larger than the EG of the material, then when that electron bumps into an electron originally at the valence band, then it will be able to knock off that electron and break the covalent bond and promote that electron to the conduction band. Now, since this original electron here gave up its kinetic energy to this other electron, then it goes down to this level. And that process is what we call impact ionization. So now we have two electrons here that still get accelerated by the strong electric field, and when both of them bumps, we get two more new electrons that get accelerated, and so the process continues, and that's why we call it avalanche breakdown. And this is actually through a continuous and amplified series of impact ionization generation of carriers within the depletion region. Now this happens when we reach some critical electric field, and we just rewrite the same equation. However, it turns out that when we compute this breakdown voltage under the required critical electric field for avalanche breakdown to happen, normally that breakdown voltage is much larger than VBI. So when we say add VBI to VBR, then VBI will be overshadowed, and we can simplify our equation to this one. Now note that we are actually always solving for VBR, and that the critical electric field is some um, defined value by the physics that happens within the material. So VBR is dependent on this one and not the other way around. Now that critical electric field is for avalanche breakdown actually ranges in this value 10 to the 5 to 10 to the 6 volts per centimeter, and it actually increases slightly with the doping concentration. And why is that so? Since if we have a larger doping concentration, then um, we'll have more scattering events within the material, and the electrons will get slightly decelerated or deflected. And to reach the same amount of kinetic energy for impact ionization to happen, um, we'll need a slightly larger critical electric field. Okay, and this is actually the correspondence between the two. The second breakdown mechanism is through tunneling, or what we call Zener breakdown. In this process, the electrons from the valence band um, will be able to tunnel through this forbidden region and get into the conduction band. Now, since we know that there are a lot of electrons in the conduction in the valence band, then um, once there is some considerable percentage that can go through this potential barrier and tunnel, then there are actually a lot of electrons that can already tunnel. Now, this tunneling is actually considerable only when the distance is around 10 to the 6, 10 to the minus 6 centimeters. So from the point of view of the electron, it sees a potential barrier, but if that potential barrier is thin enough, then it would not have to go up that energy level to get to the other point, but instead tunnel through the potential barrier. Now, this breakdown mechanism is dominant in our p-n step junctions when both sides of the junction are heavily doped, which actually helps make the depletion width to be smaller and reach this thin enough width faster. Okay, so when we apply enough reverse bias, then the plot actually, or the EBD actually becomes thinner from the point of view of the electrons from the valence band. So that's why we get to this breakdown point when we reverse bias the device. Now, the critical electric field for this to happen is around 10 to the 6 volts per meter. Now, since we are actually dealing with this thickness here, then what does the slope or the electric field have to do with that? Now, we can actually say approximate this as some triangle, where if we note that this is around, the base is around 10 to the minus 6 centimeters, and this is around, say, 1 electron volt, then the slope will be around 1 electron volt over 10 to the minus 6 centimeters, but we'll divide that by Q and get this critical electric field 10 to the 6 volts per centimeter. Now we can plug in that to our equation for VBR and actually get that the breakdown voltage for this to happen is typically below 5 volts. And since VBR is actually relatively small, then we did not actually remove this term, okay, which is around 1 volt or near 1 volt. Here we present a plot of the breakdown voltage as we vary the doping concentration on the quote-unquote lightly doped side. So here we see that as we increase N, then the breakdown voltage actually decreases. And at this portion, when the breakdown voltage is relatively large, then we can approximate the breakdown voltage to overshadow VBI, and we have this expression right here. Although this approximation may not hold at this portion. So VBR decreases with N, with increasing N, and VBR decreases with decreasing EG. So germanium actually have a smaller EG than silicon, and gallium arsenide have a larger EG than silicon. So this means that germanium breaks down easier than silicon for the same amount of doping at the lightly doped side. Now note this dashed line here, which indicates approximately where the tunneling breakdown starts. Okay, so at this portion, avalanche breakdown is dominant. At this portion, tunneling is more dominant, and we can see a tapering off of the slope. Since the breakdown voltage, or sorry, the critical electric field changes when we start going into the tunneling dominant region. Now, in terms of temperature dependence for avalanche mechanism, VBR actually increases with increasing temperature since the mean free path length changes. So what does that mean? If we increase the temperature, then it will be easier for the electrons to, or it is more common for electrons to bump through the crystal, and therefore they will have a shorter mean free path length before bumping, and if they bump earlier, then they will gain smaller kinetic energy. So to be able to reach the kinetic energy where they are able to produce new carriers via impact ionization, then we'll have to accelerate them faster with a larger electric field, which leads to this larger breakdown voltage. For tunneling, however, the breakdown voltage actually decreases with temperature. And that's because as we increase the temperature, the energy of the electrons increases, and therefore there are more electrons cramped up at these portions, which have some probability of tunneling. So if we have more electrons that can tunnel, then we'll need less voltage to be applied to reach that breakdown region. So to summarize our reverse bias breakdown discussion, if the peak electric field in the depletion region exceeds a critical value ECR, then a large reverse current will start flowing and this happens at a large negative voltage, negative applied voltage, called the breakdown voltage. So we are actually solving or using VBR as some positive quantity, and this is the expression based on the critical electric field and the doping N, which is the concentration or doping concentration at the lightly doped side. We discussed two breakdown mechanisms: avalanche breakdown and tunneling or Zener breakdown. Now, the dominant breakdown mechanism is actually dictated by the doping concentration. So if the doping concentration is very large, then the depletion widths become thinner, that it is easier for tunneling to happen. However, when tunneling is not um, not yet the dominant case, then the breakdown is actually caused by avalanche breakdown. So a bit of information, we call the diodes Zener diodes, because people back then actually assumed that it is only tunneling that occurs and did not consider avalanche breakdown. However, not all Zener diodes break down through Zener breakdown. So some of the Zener diodes is actually breaking down via the avalanche breakdown mechanism. So the next part of our discussion will be focused on RG currents, which we tried to avoid in our ideal diode analysis. So what we're referring here is the RG that happens within the depletion region. Now consider this reverse bias case, where carriers are drifting from minority carriers are drifting from one side to the other. Now, what is our expected change if there is some RG happening within the depletion region? Or to begin with, which among R or G will be dominant in this depletion region? Now note that we actually reverse bias the device, so there are less carriers present here than there normally is at thermal equilibrium, and therefore generation will be the dominant mechanism, RG mechanism, in the depletion region. So here we showed that one electron hole pair is generated. Now what happens to this electron hole pair? Now given that they are generated at the depletion region where there exists some electric field, then they will also get drifted in the same direction as the original expected carrier drift from our ideal diode analysis, and therefore this adds some reverse current. So this electron drifting to the right provides additional current that is going to the left or at the reverse direction from N to P. So there is some additional reverse bias current, meaning if we plot the diode IV curve, this is our expected curve, focusing on the reverse bias case since we added some reverse current. So instead of following this dashed line, we'll have more reverse current than expected by the model. For the forward bias case, however, this time there are, from our initial expectation, there are carriers that can now diffuse to the other side and produces our forward current. However, at the depletion region, what the dominant process now is recombination, since there are more carriers here than usual. So there are carriers here that are recombining, and if this electron here recombine along the way, then they will not be able to reach this portion. However, it is not actually these carriers that are recombining, but rather the carriers at the or nearer the band gap edges. Okay, and why is that so? Since if this electron at this energy level were to recombine to this hole here, then that would require a larger transfer of energy, which is not easy to happen, and most likely there are only a few of them. There are more electrons at this lower portion and there are more holes at this lower portion, so the most likely that will recombine are these electrons here and these holes here. Now these electrons here do not normally in our ideal analysis are not able to produce some current, but this time since they recombine, then some forward current is actually added. So instead of following our dashed line right here, then we'll have more current than expected. Okay? And that is actually depicted by these two plots right here. So at the reverse bias case, the current does not actually saturate, but actually increases slightly because of the additional current, because of the carriers generated and eventually drifting through the depletion region. Now, why is the current continuously increasing? Since if we we increase the reverse bias voltage, then the depletion region actually widens, and the wider the depletion region is, then the more area or space in which the carriers can be generated. And the larger that area is, the more carriers generated, then the more added current, reverse current we have. For the case of the forward bias current, this is actually the ideal slope expected by the Shockley model. Note that this is in logarithmic scale, and our original Shockley model says that the current is proportional to EQ VA over KT, so getting the logarithm of that should get some slope related to Q over KT. However, the diffusion, or sorry, the added current through recombination at the forward bias case actually adds some current to our diode. However, that additional current is overshadowed by the ideal current at large enough bias voltages. So the RG current for the forward bias case is considerable only when we have low forward bias voltages. So there are other things happening here. So we also this also shows some breakdown, and this sloping down here is something we have not yet explained so far, and that is actually related to the series resistance. Now let's say we have this diode here where we apply some voltage, and as we increase the voltage, the slope of the current at a logarithmic axis should be related to Q over KT, which is some constant slope. However, since there is some finite resistance at the quasi-neutral region, then some of the voltage will be dropped across these resistances, which is not anymore consistent with our assumed law of the junction, where we said that the voltage is dropped only at the depletion region. Now, what we can do instead is, let's consider that these two resistances in series were recombined and put outside here. So we now have here this ideal diode here, wherein the voltage is dropped only at the junction. However, from our applied voltage, some voltage is dropped across this series resistance. So if originally we apply some voltage VA here, then we normally expect this amount of current, or rather, let's say we use a different reference point. Say we apply some voltage here. So if this is the voltage that we apply, we expect this amount of current. However, since some of the voltage from VA is dropped through across the resistance, then the actual voltage that is dropped across the junction is some smaller V only, and the other is dropped across the resistance delta V as indicated here. So instead, we get this amount of current at this voltage instead of this amount of current. Now this plot simply shows us how much is dropped across these series resistance as a function of current. So the larger the current is, the larger the voltage that is dropped across our resistor, and therefore the larger the portion that is removed from our applied voltage. Meaning, as the current increases, then it will be actually harder for the current to increase, since a larger portion of the new added voltage is simply dropped across the resistor. And that leads to this sloping down of the current curve. Another phenomenon that actually causes the current to decrease at very high applied voltages is through high level injection. Now, as we increase VA, then from our thermal equilibrium value, the amount of minority carriers we are injecting actually increases and increases until we reach some point wherein low level injections does not anymore hold, and we enter this high level injection. Now, what happens under this high level injection? Note that originally we drew the majority carriers as some constant plot. Okay, so for example, this one originally was this one under low level conditions. However, at high level injection conditions, the majority carrier concentration is now perturbed. And why does their value change? And that is because to maintain charge neutrality within the quasi-neutral region, if there is too much excess minority carriers, then the majority carriers will start increasing to maintain charge neutrality. And with this sloping of the majority carriers, then say what do we expect now? Since we have this sloping of the majority holes, then holes will start actually diffusing leftwards, okay, from the N side to the P side, which is actually um, the reverse direction. So instead of getting more current, um, this sloping here produces a current that counteracts the original forward current, and that's why we get a slightly smaller current when we enter this high level injection bias range. So here we say that at high level injection there is significant gradient or slope in the majority carrier profile. That majority carrier diffusion starts reducing the current from expected by the ideal diode equation. Now, adding up all the non-idealities we have discussed so far, at the reverse bias case, instead of actually saturating at I naught, the reverse current actually increases as we increase the reverse bias voltage because of generation in the depletion region, which carriers are generated and drift through drift across the depletion region, adding to the reverse current until we reach some applied voltage minus VBR, where the diode enters some breakdown region and the current starts increasing abruptly. Now, for the forward bias case, at low forward bias voltages, there is considerable additional current due to thermal recombination at the depletion region. However, that will be overcome by the ideal current at this portion. But as we increase VA, we start experiencing high level injection where the current is slightly decreased, and once the current is very large, then um, the series resistance starts playing a major role in sloping down the current. So this is um, what we get with a real diode. For the next part, we'll start the modeling of the diode under small signal. So consider this diode. Here we apply some DC voltage and therefore get some DC current. However, when we add some small small AC voltage that is a function of time, then we'll get this small additional current right here. So let's say the small signal that we add is some sinusoidal voltage with some small amplitude here. So the voltage will oscillate around this DC value and given by the amplitude VA. Now, if the change in voltage is slow enough that the diode can actually follow its DC IV curve, then we'll get some sinusoidal current passing through the diode, and that is added on top of the DC current. Now, note that the amplitude of the additional current is related to the amplitude of the input current via the slope of the curve at that point. So if we consider this applied voltage slow small enough, That's why we call this small signal model. Then this line actually looks like a perfect flat line when zoomed in enough. Then the relationship between these two is linear, and that linear relationship is through what we call the small signal resistance of the diode. So here we represent the diode at small signal as having some small signal resistance, and in addition we'll also discuss that the diode actually have some small signal capacitance. So the small signal current from the small signal voltage is actually related by this equation by KCL. So by KCL, this I is equal to VA over R plus the voltage across our capacitor is C, or the current through our capacitor is C dV over dt. Now the small signal conductance, let's start with conductance first. G is the reciprocal of the small signal resistance R, and this conductance here is actually defined as the slope of the IV curve. So since that is the slope, then at this portion G is 0, which means R is infinite. At this portion slope is high, G is high, so R is small. Now if we perform the derivative, then the derivative of negative I naught is 0. So we're left with the derivative of I naught EQ VA over KT. So we get the same expression here, but by chain rule, we get this additional factor at the denominator, KT over Q. However, at forward bias case, this is approximately equal to IDC over KT over Q, because at forward bias, this term here is approximately negligible. So we end up with this one here, and since this one is approximately this one, so that means this one is approximately IDC. However, we cannot use this simplified equation here at reverse bias, since at reverse bias this minus 1 here is the one that is actually dominant. And if we follow this at reverse bias, then IDC at reverse bias is minus I naught, negative of the reverse saturation current, and therefore we'll get some negative G, and so negative resistance. However, what we are expecting is some positive large valued small resistance. However, if when we stick to this forward bias case, this simply tells us that okay, the conductance actually increases linearly with the current. So the resistance is simply KT over Q over I. So that's the small signal resistance. Moving forward, we'll now discuss the small signal capacitance. However, this capacitance is unlike our usual capacitance, and instead we'll define the small signal capacitance based on the incremental amount of charge we get for every incremental voltage that we applied. So we actually get dq over dv, and not exactly q. Okay, we get the incremental q per incremental voltage. So there are two sources of charges in our PN junction. First is the minority carrier charge when we change the bias of our diode, we are actually storing some incremental charge within the quasi-neutral regions. However, this charge is quasi looks like we're maintaining this charge, but this charge is actually recombined but are just replenished every now and then by the current through the device. This depletion charge is actually some charge related to the depletion region due to the absence of carriers at the depletion region. Again, we are not will not deal about the total charge here, but rather the incremental charge for the small signal capacitance. So these two charges here actually result in two different small signal capacitances. So the first one is what we call the diffusion capacitance, based on the minority carrier charge stored at the quasi-neutral region. And this is called the diffusion capacitance since this is related to the diffusion currents. Okay, and these charges are actually diffusing within the material but are just replenished every tau. Now, since this is some small signal capacitance, so we are actually talking about the incremental charge. So say we apply some incremental voltage delta V, which is positive, then this carrier concentration or excess carrier concentration will actually change and will get slightly more charge. Now, if we apply some delta V that is less than 0, then we'll get slightly smaller amount of charge. And so, if we apply some sinusoidal delta V of some magnitude, then the differential charge we are actually talking about is this charge right here, and not the current DC charge or steady state charge we have. Now, for the depletion capacitance, we'll denote that as CJ because this is related to the junction capacitance. So this is CD for diffusion capacitance. This is CJ for junction or depletion capacitance, which is due to the variation of depletion charge. Now, if we apply some positive delta V, then we'll get that the depletion region should actually shrink by a little amount. And if we apply some negative voltage, then the depletion region will actually widen by some amount. And the incremental charge we're talking about is this incremental charge here for every incremental voltage that we apply. Now, starting with our diffusion capacitance, let's say we consider a one-sided junction, P plus N. So assuming that the P side is at the left side and the N side is at the right side, then P plus N will have a very large majority carrier concentration and a smaller at the P side and a smaller majority carrier concentration at the N side, and therefore the thermal equilibrium values for the minority carrier concentration will be very small at the P side and slightly larger at the N side, and therefore when we apply some, say, positive um, positive voltage, then we'll get this small amount of additional charge here and a larger amount of charge here, and therefore the total charge stored is actually dominated by this QP. QP to denote the charge due to holes, okay, and not the charge at the end side. So this is the charge due to holes, and that is the dominant one, considering the total charge within the device. Now that charge is actually related to the current, and if we divide that amount of charge by tau, we actually get the DC current. So for the diffusion capacitance, we need to get the incremental amount of charge for every incremental amount of voltage. So we solve for Q here. So Q, which is approximately QP, is equal to I tau P. So if we get the derivative of that, we'll get tau P delta I for every delta voltage VA. So now this derivative of I with the applied voltage is actually how we have defined the small signal conductance, and therefore we can perform the integral and show that the integral of the current with respect to voltage is this one, and therefore this is our expression for the diffusion capacitance. Now at forward bias, we have shown that this one is approximately equal to IDC. So this is a more simple form of the diffusion capacitance. Now for the junction capacitance, the incremental charge actually appears around the edge of the depletion and quasi-neutral regions, and that incremental charge makes this device actually look like a parallel plate capacitor with an with a spacing equal to W, with the depletion region acting as the insulator. And so we expect that this capacitance should follow this form epsilon A over D, where D is the depletion region and epsilon, or the dielectric constant, is the permittivity of the semiconductor, since this one is a semiconductor, or for the case of silicon, this one is the permittivity of silicon. Now for some exercise, say we want to reduce this depletion capacitance, then what can we do? Say we have a fixed material, so this epsilon S will not change anymore. To decrease the depletion capacitance, then we can decrease the cross-sectional area. But if we don't want to decrease the cross-sectional area, the only way to go is to increase W. Now, to increase W, what we can do is to reverse bias the device. So actually reverse biasing the diode widens the depletion region, and that decreases Cj. However, if we say we have some fixed target applied bias and we want it to be forward bias, then what we can do is actually to decrease the doping concentrations. The opposite one is when we increase the doping concentration. When we increase the doping concentration, W decreases and the capacitance will increase. This also tells us that we can actually reverse bias the device, and um, get a capacitance that is a function of the applied voltage. So um, when the PN junction is actually reverse biased, we can actually um, operate the diode as some varactor or variable capacitor. So now we know that the small signal capacitance of the capacitor has two components: the junction capacitance, which is um, the parallel plate capacitance, and the diffusion capacitance related to the um, charge at the quasi-neutral regions, and they are actually acting um, in parallel. So we simply add them. Now we know that CD dominates at moderate to high forward bias. Since if we forward bias the device, then um, this current actually increases exponentially, and that can easily overshadow this one. Although we note that CJ also increases with the applied voltage, since increasing the applied voltage decreases W, which increases CJ. However, the increase is actually faster for the case of CD. Okay, so now at the other um, side, at low forward biases and at reverse bias, CJ is the one that dominates, since this term here is actually smaller at this portion normally. Okay? So now let's consider a one-sided junction under some reverse bias. So we noted a while ago that at reverse bias, um, C is equal to Cj plus Cd, but at reverse bias, the one that dominates is the junction or depletion capacitance. So this one is related to epsilon SA over W. Now let's say we take the reciprocal of that and square it. So we get the reciprocal of this and square it. So we get W squared over A squared epsilon S squared. And we can actually show that this one is approximately equal to this one from this equation. So W is equal to square root of 2 epsilon S VBI minus VA over Qn, where N is the doping at the lightly doped side. And this equation here is valid for one-sided junctions. So if we square this one and substitute here, we get this equation right here. Now this is quite interesting and actually tells us that if we plot this 1 over c squared, then we get this linear plot whose x-intercept is VBI and having a slope that is proportional to the doping concentration at the lightly doped side. Now, how do we use this information? So when we have our diode already fabricated, what we can actually easily say measure is not the doping concentration, not the built-in voltage, but rather say apply some current and apply some voltage. Now if we apply some small signal voltage, and if we check the small signal current, then we'll actually have some idea with the small signal resistance and small signal capacitance of the diode. And if we plot that at varying DC reverse bias DC voltages, then we can actually get this plot here. And from this one, if we know the area of our diode and the permittivity, then we can actually um, indirectly measure or have an idea of the doping concentration and eventually plot the doping profile of our diode using this information. Okay, and we can also actually approximate the built-in voltage as the x-intercept of this line. However, note that this equation right here is only valid at this portion where Cj is dominant. And if Cj is dominant, then we can use um, this equation. So looking back, we actually said that at um, up to a small forward bias, Cj is dominant. At this portion, Cd starts playing a role, and we cannot anymore say that this C is only Cj. So in addition to that, we can actually add some series resistance here. That series resistance is the same resistance for DC. If you look back from EEE 33, the AC resistance of a resistor is the same as its DC resistance. So we can just put that in series here. Then after we have removed that resistance, we put the series, we put the small signal resistance or conductance in parallel with the small signal capacitance, which have two components, Cj, the depletion or junction capacitance, and Cd, which is the diffusion capacitance. We have these expressions right here. This is valid at any um, bias condition. However, this expression here is valid only at forward bias, and we will not anymore show a expression for reverse bias, since either way Cj is the one that dominates. So in summary, with enough reverse bias, the diode will enter a breakdown region where reverse current suddenly increases. This is caused by impact ionization, which leads to avalanche breakdown, or tunneling, which is the dominant process in Zener breakdown. Now, there is also a case where both of them is both happening and considerable. So we put this and or. Now, the current in an actual PN device will not exactly follow the Shockley equation, even with ideal step junctions, and this is due to breakdown, thermal RG currents, high-level injection, and series resistance. So the last part of the lecture, we show that at small signal, the diode can be modeled as a small signal resistance in parallel with a small signal capacitance, sometimes with a series resistance. Now, the small signal resistance and the small signal capacitance are both dependent on bias, since changing the bias changes the slope of the IV curve, changes the amount of charge, additional charge we get for some additional voltage, changes the depletion region width, and so that is the cause of the change with bias. So the DC bias actually influences the AC characteristic of the diode. Now we have two sources of capacitance: junction or depletion capacitance and diffusion capacitance. And we have actually discussed the cause of these two. Okay, so that's the end of this lecture. Thank you very much.